Welcome to today's Explainer. We are going on a really fascinating journey to decode the hidden, invisible mechanics of the universe. We're going to look closely at the secret life of gas molecules. We'll explore how they move, how they interact, and most importantly, we are going to use some beautiful step-by-step math to derive the average translational kinetic energy of these molecules. And trust me, we're going to do it in such a simple conceptual way that literally anyone, even if you've never taken a physics class in your life, can totally understand what these molecules are doing right in front of us every single second of the day.
Okay, let's dive right into this. Have you ever stopped to think about what popping popcorn and the heavy, super firm tires on a semi-truck actually have in common? I mean, on the surface, they seem completely unrelated, right? One is a delicious, buttery movie snack, and the other is a heavy-duty piece of rubber supporting literal tons of metal. But as you'll see today, they are actually both governed by the exact same hidden life of gas molecules. Here is our roadmap for today. We'll start by comparing the macro and micro worlds, look at the constants that connect them, step through that kinetic energy derivation, find out how fast these molecules are going, and finally, apply it all to daily life. So starting off, we essentially have two completely different perspectives for looking at the exact same gas.
On one hand, we have the macro world. This is the big picture, the world of things we can actually measure and feel. For this, we use the ideal gas law, PV equals nRT. P is pressure, V is volume, lowercase n is the number of moles, R is the universal gas constant, and T is temperature. You know exactly what a hot temperature or high pressure feels like. But then we have the micro world, which relies on the kinetic theory of gases. That equation is PV equals 1/3 nmv squared. Here we're zooming way in on the tiny, invisible, chaotic stuff. Capital N is the total number of molecules, m is the mass of just a single molecule, and that v squared represents their mean square velocity, basically how incredibly fast they are zipping around. Notice how both equations equal pressure times volume, or PV? So the big question is, how do we link the temperature we feel on a hot summer day to the microscopic speed of those tiny molecules?
Well, let's move forward and see how this builds because we need a bridge to close that gap. Enter the Boltzmann constant, usually written as K sub B. Now, don't let the fancy name intimidate you. Think of this not as scary math, but simply as a translation key. We have the universal gas constant, R, from our macro world, and Avogadro's number, N sub A, which is literally just the number of molecules in 1 mole from our micro world. If you just divide R by Avogadro's number, you get this beautiful new constant, the Boltzmann constant. It is the ultimate bridge that lets us convert macroscopic moles into microscopic molecules seamlessly.
All right, here is where the fun really begins. We are going to derive the kinetic energy of a gas step by step.
Let's watch how this macro equation transforms. First, if we take our macro equation and simply replace the number of moles, that lowercase n, with the total molecules, capital N, divided by Avogadro's number, look what happens. We substitute that right back into the ideal gas law. So PV equals nRT becomes PV equals n over n sub A times RT. Now look really closely at that middle part. We suddenly have R divided by N sub A just sitting right there. And as we just learned a second ago, that is our translation key, the Boltzmann constant. So we swap that out, and our macro ideal gas law beautifully transforms into PV equals N times K sub B times T. Now, what's really interesting about this is that we suddenly have two equations that both equal pressure times volume. Our newly transformed macro equation is PV equals N K sub B T, and our micro equation from earlier is PV equals 1/3 nmv squared. Since they both equal the exact same thing, PV, we can literally just set them equal to each other. Look at how elegantly this math unfolds. It's like a giant puzzle snapping together. We have a capital N on both sides, so those just cancel out completely. Goodbye, total molecules. Now, remember basic physics? The famous formula for kinetic energy is 1/2 mv squared. Right now, on our right side, we have 1/3 mv squared. Close, but not quite. To make the correct formula up here, we simply multiply both sides by 1/2. And boom, the kinetic energy formula magically reveals itself right in our equation. We have successfully uncovered the hidden kinetic energy of a gas molecule. And when the dust settles, we are left with a triumphantly simple expression on the left side. 3/2 K sub B times T. That's the whole shebang. 1/2 mv squared, which is the average translational kinetic energy, is equal to exactly 3/2 K sub BT. So the crucial point is this. Because 3/2 and the Boltzmann constant are just fixed numbers, the only actual variable left over is temperature. This means the average translational kinetic energy is directly proportional to the absolute temperature of the gas. If you turn up the heat, the molecules simply move faster and smash into things with way more energy. If you cool it down, they get super sluggish. It's a direct, unbroken mathematical link between the temperature you feel on your skin and the microscopic speed of the universe.
Since we know their energy now, we kind of have to ask, exactly how fast are these tiny particles actually going?
We can figure this out by taking our cancel-down equation and just isolating the velocity. We move the 3 and the mass over to the other side. That gives us velocity squared equals 3 k sub b t divided by mass. Then you simply take the square root of both sides, which gives us what physicists like to call the root mean square speed.
And here we have it, our final equation for root mean square speed. VRMS equals the square root of 3 k sub b t, all divided by m. So what does this equation actually tell us in plain English? Two really intuitive rules. First, higher temperature means faster speed. Heat them up, they zoom around like crazy. Second, heavier mass means slower speed. This is an inverse relationship because mass, that little m, is at the bottom of the fraction. Think about it. Heavier molecules, like oxygen, are physically harder to push around than super light molecules, like hydrogen. So at the exact same temperature, heavier gases are just going to move slower.
All right, let's bring all this abstract math back to reality to deliver the payoff for our initial hook: popcorn and tires. What we've just arrived brilliantly illustrates the physics of popcorn. Inside every hard little popcorn kernel is a tiny bit of trapped moisture. When you put it in the microwave or on a stove, you are adding heat. That heat turns the liquid moisture into steam, which is a gas. As the temperature T continues to rise, our newly derived formula guarantees that the kinetic energy of those gas molecules skyrockets. They start flying around at incredible speeds, violently colliding with the inside walls of the kernel shell. This creates massive pressure, until eventually the shell simply cannot hold it anymore and it violently bursts open, giving us our fluffy snack. The exact same microscopic mechanics apply to car tires. You know, a truck tire supports tons of weight, not because rubber is magically strong, but purely because of gas molecules. When you pump air into a tire, you are drastically increasing the number of molecules, or capital N. More molecules mean millions and millions of more frequent collisions against the inside rubber walls of the tire. These continuous, relentless, microscopic impacts push outward with immense force, creating the massive pressure required to keep a heavy truck from sinking right down to the pavement. So we've learned that increasing the temperature increases the kinetic energy, which in turn violently increases the pressure as those molecules smash into their container faster and faster. Let me leave you with this final provocative thought to test your new knowledge. When you're driving really fast on the motorway, the friction between your tires and the road creates a massive amount of heat. Based on everything we just learned about temperature, kinetic energy, and gas pressure, why do you think car tires sometimes suddenly burst on a hot summer road trip? Think about what those little gas molecules are doing inside. Thank you so much for joining me on this explainer, and I hope you never look at a popping kernel or a rolling tire the exact same way again.